All right, so here is the homework for the electric field stuff that we did yesterday. So I'm gonna go through this and see if you could figure this stuff out. Um, okay, so for the first part here is drawing the electric field lines. Again, you couldn't really input this into the thing, um, but what you should see is the protons and electrons. Since you have a positive and a negative charge, you should get a line that is something like here. I'll just pull up an image of it. Hold on, this one. Yeah, you should get something like this, right? Positive electron or positive proton, negative electron. You have the field going between them. It'll look something like this. The exact number of lines can be different, but since their charges are equal, the number of lines should be the same. So, yeah, that should just be how that is normally there. Get something like this. It doesn't matter which side they're on, but yeah. Okay. Oop, what's this one? Okay. So that's kind of what that looks like there. Now for B, what is the strength of the electric field created by the proton at the electron's position? Okay, so finding field strength, it's KQ over R squared. And so let's be careful about the numbers here. We have, K is 9 times 10 to the 9. And then we have the charge, and this is the charge that creates the field. Okay, so for B, the strength of the field created by the proton. So 1.6 is 10 to the negative 19. And then divided by the distance. And the distance is, well, we're wanting to know the strength of the electric field at the electron's position. So the distance is going to be, well, the difference in size between them. So that is going to be your 10 to the minus 10. Oh, and it's squared. So let me move the parentheses here. Okay, you get something like this. So yeah, so we got all this. Okay, so let's think about numbers here. We have 9 times 10 to the 9, and then 1.6 times 10 to the negative 19. So 10 to the 9, 10 to the negative 19. That ends up giving you 10 to the negative 10. Pull the calculator also. Okay. So we have, let's just multiply these two up here. So we have 9 times 1.6. So it'll be 14.4 times 10 to the negative 10. Now, I know that's not incorrect scientific notation, but I'll deal with that in a second. And then we are dividing by 10 to the negative 10 squared, which is going to be 10 to the negative 20. So we have 10 to the negative 10 divided by 10 to the negative 20, so that becomes 10 to the positive 10. And so 14.4 times 10 to the 10. And then we got to move the decimal over, so this is actually 1.44 times 10 to the 11 newtons per coulomb. Okay, so that is the strength of the field created by the proton at the electron's position. So again, big number, right? I said this earlier, how your electric field numbers are usually going to be pretty big. Again, this is a pretty extreme example. Well, I mean, not really actually, because we're just talking about protons and electrons, and this distance scale in angstrom. That's kind of a scale that's used for atoms a lot. So this actually is a reasonable number, even if it seems ridiculously big. But yeah, so that's your answer for that. Okay, so then C. What is the electric force on the electron? Okay, so now we're saying, all right, so we have the field here created by the proton. What is the force that the electron feels? So the whole thing for this is that we're taking what the field was and multiplying it by the new charge. So now we have here the charge of the electron, as that's the new one, and again, this is your negative 1.6 times 10 to the negative 19, times the strength of the field, which is what we just got. And let's see. 1.6 times 1.44. Well, here. Times 1. What am I doing? 6. Okay. 2.304. And the exponent's negative 19 to put in positive 11, so that becomes negative 8. Let me 100% make sure that I can do exponents correctly, because I messed it all up earlier yesterday, so there you go. But yeah, that lines up that way. So again, even though your electric field strength is really big, because we're talking about, single protons and electrons here, the force is pretty small. So it does actually make sense ultimately the force is going to be small. Now the negative, that would come into play. Of course, you'd say, oh, I have a negative force. But remember, that's deals with direction. So basically what I'm saying with this being negative is that whichever direction this field is, which we didn't specify, and the reason why we didn't specify is because I don't specify, like, the protons on the left or the electrons on the right or whatever. I didn't specify that. So the point of the negative is just saying whichever direction the field is pointing, the force is going to be in the opposite direction, right? And think about this. So this was the field from the proton, and since a positive charge, the field is outward. Okay, so the field's going outward, but you have the force on an electron. Now, the field's pointing outward, but if you put an electron next to a proton, opposites attract, right? So it's going to want to go towards the proton. So that's why it's negative. It's basically saying the field is going away from the proton, but the electron's going to do the opposite. That's why it's negative. So it's going to come towards it. So that's sort of how you can specify that there. Okay, so then, explain why this is the same as the electron force on the proton. So this is the force on the electron from the proton. Now to do the opposite, what we would have to do is to find what is the field strength from the electron, and then find the force on the proton. And the explanation here is that if we do this, find the force on the proton, we do the exact same math, right? Nothing has changed mathematically. It's just you do things kind of in a slightly different order. You would have the negative as part of this, and then this would be positive, so your force would ultimately be the same. So because of that, the forces are the same, and that kind of makes sense, right? It's just how, like, the force of gravity on the Earth is the same as the force of gravity on the moon. The difference is kind of what we're going to now for D. So D says, okay, the mass of a proton is blah, and the mass of an electron is blah. What is the acceleration of the proton? Okay, so again, the forces are the same, but because the masses are different, you get very different accelerations. So this is simply that F equals ma. So therefore, therefore A equals F divided by m, right? Only did lowercase m for consistency. So the force that we have, we just calculated that. Again, the negative here doesn't really matter. I'm just going to kind of get rid of it, because again, the negative just told you about direction, and we know what the direction is. We know that they're going to move toward each other, right? So 3.04 times 10 to the negative 8 now. I'll keep doing the parenthesis thing. I keep going to do that. And then we're going to be dividing by the mass of the proton for this first one. So that is 1.67 times 10 to the negative 27. So A equals, whatever that is, 2.304 divided by 1.67, and you get, oh boy, I'll just do 1.38 as a rounding. And exponents, negative 8 minus negative 27, so that would be 19. I don't trust myself. Negative 8, whoops, wait, hold on. I can't do minus as a substitute for 8, so negative 8 minus negative 27. Okay, 19. Yes, I don't trust myself with exponents anymore. So yeah, that's your acceleration of your proton. You might think that's a ridiculously big acceleration, and yeah, it kind of is. Yeah, it's kind of a lot. Now, because of this, you might think, isn't that like could be an issue about, like, getting past the speed of light? And it would if the time intervals here weren't like unbelievably tiny, right? This is like how much time does it take for protons to touch electrons? It's a stupidly small amount of time, right? So it actually ends up being okay. So the fact that your number is that high is actually fine. So E, exact same kind of thing. Only difference being that now we are going to use the electron mass instead. The force is the same. Divided by the electron mass, 9.11 times 10 to the negative 31. Okay, and so we get... Oops, I'm running out of things. Okay, so 2.304 divided by 9.11 gives you 0.253 times 10 to the negative 8, and this is minus negative 31. Again, I don't trust myself. So negative 8 minus negative 31, 23. Difference here is that since, again, we're off with the scientific notation, so we want this to be 2.53 times 10 to the 22. That's our answer. So this is why, sure, again, the forces are the same, but, I mean, these accelerations are both very large, but the electron is, still like almost 2,000 times bigger than the proton, hence why the electron moves around the proton and not the other way around. So just kind of showing how that works there. And again, these big numbers, yeah, that's what we actually get. So there you go. Okay, so that's number 1. Moving on to number 2. Oop, let me just get you all fully on the next page. Okay. Oop. Okay, there. So now we have the charges of the proton Earth and the electron Moon calculated from yesterday's stuff. Okay, so the A, what are we doing? Okay, calculate the strength of the electric field created from the Earth at the Moon. Okay, so this is going to be the field created by the Earth. Let me label this as part A. Okay. So we need the charge, because it's created by the Earth, so we need the charge of the Earth, what we got before, which is whatever it was all the way up here. This. This is our charge of the Earth, so copy that. Go all the way down to here. Oh, why do I always add the space like that? Okay, no, I don't need the Coulomb symbol. Okay, then divided by the distance squared, which is 3.844 times 10 to the 8 squared. Okay, that's a fun equation. So we have the field created by the Earth. Okay, let's just look at the top part first. So we have 9 times 5.72. 51.48. Okay. Times 10 to the, let's see, 9 plus 32. I trust myself with that to be 41. However, because this is 51, I need this in correct scientific notation, so it's going to be 5.148 times 10 to the 42 divided by this squared. So 3.844 squared. I'll do 14.776 times 10, and you're squaring the 10 to the 8, so it becomes 10 to the 16. But since we gotta move this down, that means this is going to be to the 17, and then we can divide this. So we get the field strength of the Earth equals 5.148 divided by 1.4776. 3.484 times 10 to the 42 minus 17. Again, I'll just be super careful and just do it. 25. Okay. There's your electric field strength. And again, since the Earth is a positive charge in this example, this field would be going away from the Earth. So that's the strength of that there. Yeah, okay, now B, find the strength of the electric field created by the Moon at the Earth. Okay, so now we're doing the reverse. We're now finding the field of the Moon where the Earth is. Now, for the proton and electron example, it didn't change the math because the charge of a proton and electron, the actual number, not the sign, is, it was the same. So we didn't really have to change the math. But here it's different, right? This was the charge we got for the Earth. So the charge for the Moon is here. That was the charge of the Moon. So we want to use that instead. Again, the negative doesn't really matter in this case because that just deals with direction, and we're not really worried about direction right now. Okay. And then that's divided by the same distance. 10 to the 8 squared. Okay. E moon equals. Alright, now I multiply the stuff out again. So 9 times 1.29 gives you 11.61 times 10 to the 9 plus 34 gives you 43. However, again, we got to move the decimal over. So this becomes 44 divided by that squared, which, well, that's the same. 1.47 times 10 to the 17. Okay, so we have that divided by 10, divided by 1.4776. It's not a great number. I'll do 0.7857. I'll do that. Was it 7857 times 10 to the 44 minus 17 is 27. Yes? I so don't trust myself. Okay, yes, 27. But again, we gotta move this over, so this is going to become 26. Yeah. And does that line up pretty well? Yeah. So the difference here is, again, that we change the charge value. So remember how this charge was about 20 times this charge? That means this field should be about 20 times this field. And yeah, it's pretty close. It lines up well enough. So this seems to work. Those are our two field numbers. So then C is to calculate the force between the Earth and the Moon. Okay. Now, we can use either of these two field numbers. It doesn't matter, right? Because the force is whatever is you take a new charge and you put it into a field. So we could either say, well, this is my field created by the Earth, so I can multiply it by the charge of the Moon, right? The other one. Or I can say, this is the field created by the Moon, I can multiply it by the charge of the Earth, right? And you'll get the same answer either way. So it doesn't really matter which one we pick. I'll pick the field of the Earth, so therefore I want to multiply by the new charge of the Moon times 3.484 times 10 to the 25. Okay, so this is what I get with this here. And as you can see by your exponents, this is going to get kind of absurd. So 1.29 times 3.484 gives you it's 4.5. Close enough. And then we have 34 and 25 as your exponents. That becomes 59. That's our force. Now that's a little absurd. You're not going to really get anything to work with that there. That's your answer. You can see why this gets kind of ridiculous. So this makes these accelerations not look too ridiculous now anymore, does it? So, well, actually, okay, I'm going to keep... you don't have to do this for the question. You're done with the question, but just to kind of elaborate from this. So what we could do is say, okay, if our orbit, if this was an actual thing, how fast would the orbit of the Moon be going around the Earth? How fast actually is that? So to do that, we have to find the acceleration. Again, this is supplemental. I just want to show you this. So, just for fun, let's just say that the A is going to be the force divided by the mass. So let's look at the mass of the Moon. So we have 4.5 times 10 to the 9. We want to divide by the mass of the Moon, which is something that I put away up here. I don't remember. Mass of the Moon. This was the mass of the Moon. We're already so many pages in. Okay, there's your mass of the Moon, and you end up getting. Okay, I'll not round that. 7.348. Just get a more accurate answer. 0. I'll do not a great number to round. You know what? I'm gonna actually put all of this in. I can. And paste. Yeah. Okay. So then times 10 to the, let's see, 59 minus 22 is 37. But I need to move this over, so this becomes 36. And then, oh wait, there was a, why did I close the calculator? I'm stupid. It also means I left what number I had. Yeah, that was really dumb. Why did I do that? um. Okay. Uh. Hold on. Let me just double check this to make sure I'm doing things right. 7.348. Wait. Oh, because it's rounded, right? Uh. Yeah. You know what? Screw it. Let's just do the rounding. So 6124. I'll do that. There. Anyway, that's our acceleration of the moon. And we did this. We had, if you remember, it was centripetal acceleration. You could find the speed of something that's moving around in a circle, and so that was that the acceleration equals v squared over r. So therefore, v equals the square root of a times r. So we have the square root of a, which we just got, 6.124 times 10 to the 36, times the orbital radius, which is this up here, 3.844 times 10, 8. And close that parentheses. Okay, so what do you get? You get that v equals the square root of, there's a point to all this, trust me. Besides just random garbage. Again, you don't need to do this for the homework. I just want to show you because it gets to a point. Okay, so we have 6.124 times 3.844. That gives us 23.54 times 10 to the 36 plus 8 is 44. So I'm okay. I would normally, make this be correct scientific notation, but we can actually take advantage of this because square rooting is, remember, dividing the exponent by half. So if we keep this, then we can just say that's, well, 10 to the 22, which means we can just take the square root of 23.54. So what is the square root? Where's the square root symbol? Do I have to do this? Yes, I do. 4.85. Okay. So the point of all this unnecessary extra work was to show that if this moon-Earth proton-electron thing was the case, the moon would be orbiting around the Earth at a speed of this. Remember that the speed of light is 3 times 10 to the 8, so this is a lot more than that. If you want to go a step further, you could also figure out how much time would it take to go around the Earth, and so you could do that by doing, actually the time would be, basically 2 pi r of the radius divided by that velocity. So you get 2 pi times 3.844 times 10 to the 8 divided by that ridiculous number. And you get, okay, so 2 times, where's pi? Pi times 3.844 divided by 4.85. Okay, that's basically 5. So that gives you 5. And then we have 10 to the 8 divided by 10 to the 22, which is negative 14 times 10 to the negative 14 seconds. Okay, so in other words, if the moon was all made of electrons and the Earth was all made of protons, they would orbit each other to the point where the moon would be going like almost the speed of light cubed, and that the Earth, it would take, 5 trillionths of 5 thousandths of a trillionth of a second to orbit around the Earth. So completely insane and ridiculous, which is kind of the point of this. But anyway, this is all extra crap that is not that important. But I just thought it was interesting to show you how ridiculous these numbers can be. So there you go. You learned a thing, I guess. I don't know. I'll just delete that just not make it confusing. Okay, so let's actually move on to the point of today, which is, trust me, not this video is not going to be nearly as long as what yesterday's was. If anything, what I just went over for the homework was probably most of the video. But so today I have an electric field simulation lab. Now the link to that is in the classroom post, and so you can kind of have that sort of there. There's also a document which is the lab basically that I have attached as well. Now, Before we get started with that, though, I do have a warm-up question for you. So let's get into that. Your warm-up question is, can the electric field strength be zero between two charges with the same sign? So they're both positive or they're both negative. Or what about if they have opposite signs? So one's positive, one's negative. Basically, just yes or no. Excuse me. Yes or no for both of those questions. Can it be zero if they're both positive or both negative, and you're somewhere between them? And then yes or no, can it be zero between if you have one positive, one negative? So pause this, think about this. You could maybe look up the images of the electric field lines and think about it for a little bit. Okay, so hopefully you remember what these kind of look like, or I can just show you. Actually, I can show you with just this image here. So if they have like charges, right? If they're both positive, if they're both negative, the field lines curve away from each other. So because of that, there will be a point somewhere in the middle where the charge is zero. Even if this charge is like 100 times the charge of this charge, if they're both positive, then there will be a region where the field is zero. Now, if this charge is much stronger than this charge, the 0 point will be closer to the weaker charge, right? But it will be in here somewhere, okay? Conversely, if one's positive and one's negative, you can never have it be zero somewhere in the middle. It just is not going to happen. If you only have two charges, if you have more than two, then I guess it could happen. But if you have two charges, there is no region where the field is going to be zero in the middle, and it's just not going to happen no matter what. Again, if this one's way greater than this one or whatever, it's not going to happen. So the answer are that if you have it can never be zero. I should clarify it. The electric field can never be zero between two charges with opposite sign, but it will always be zero in a point. I'll say at a point. At a point between two charges with the same sign. Okay. And again, where that point is, where that 0 point is, depends on what those charges are. But you can see how that works with that. Okay, so this whole idea of like the shape of the electric fields and what they look like, that's the point of the lab. So open up or get the link going for the lab, and you should end up to this kind of page here. This is your lab. Now, there's kind of a lot here to look at. A lot of this you don't really need. What you should do is definitely have values turned on, and you could put on the grid if you want, but that's not necessary. I'll leave it on just to be more precise. So, but yeah, the other stuff you don't need to worry about. Do not click this. And also the voltage you can mess with if you want. Again, we haven't talked about voltage. It looks cool, but you don't, there's not really a point to it at this point because we'll learn about voltage later. So how this works is you click and drag one of these charges and you just place it somewhere. So let's say you place it there. Okay, there's your field. Okay, so we have a positive charge and the field is all going away from that positive charge. Okay, and so you can see how that works. Now, and you can probably notice that some of these arrows are brighter than others. And so where the arrow is the brightest, closer to the charge. So the brighter the arrow, the stronger the strength of the field at that point. Now, this yellow thing here is if you put it there, it tells you which direction the field is at that point, and it also gives you a strength number. So this V over M, this is another unit which is used for electric fields. So we had newtons per coulomb. This is actually volts per meter. That also is totally fine. Okay, so this actually works for electric field as well. Again, we'll talk about volts later. But that works here. So don't worry too much about this. But the number itself is not that important. But you can see as we move it closer in, it gets, stronger and stronger. And you see the length of the red arrow increases. The red arrow is basically, it's the vector of the electric field at that point. So it's pointing, so the red arrow points at the direction of the field at that moment, and also gets longer as you get closer and closer in. And of course, as you get like really, really close in, then it gets to, like infinity, and then you get to ridiculous numbers. Like, yeah, there's 146,000 or whatever. I get any higher? I don't think so. Ooh, my mouse is sensitive. Oh, wait. Oh, I got right on it. Okay, so there's my, there's your undefined. All right. So anyway, you can kind of you can see, woo, so it kind of looks kind of cool. Now you can combine things though. So for example, I can put a negative charge here. Okay, and so here, let me move this out of the way for a second. You can see you have the field sort of bending from the positive into the negative charge, and you can see this overall shape of how that works. And so you can kind of mess with this and see, okay, so here's the field going in negative. It's pointing towards the charge, and you can kind of all see how it's pointing in total. And again, it follows the arrows. So, and you can see here, you can as to why the warm-up question, why you can never have a 0 point between two unlike charges of opposite signs. You can kind of see that with this, right? This is never going to be 0. If anything, it's like really big kind of between them, right? So that's never going to really happen. And you can kind of keep messing with this. You can add, what about if I add another charge over here, right? There's another negative. Or what about if I have a, let's see if I switch this out for, well, actually, let me put this back. I can take this out though, right? And just have the positive. I can have a positive over here instead, right? So here you can see, now with two positive charges, you can see that the fields kind of cancel out and I can get to a 0 point like right here if I do it right. So close. Maybe not. Anyway, there is a 0 point like right about here, right? There actually this negative charge is affecting it slightly, but very slightly. So you can mess with this and see how this all works, and it's kind of neat. Again, the voltage thing is not something you're going to be dealing with in the lab itself, but if you want to see it, it does look cool. It just kind of gives you a little color aspect of it. So if you want to kind of mess with this, you can put as many of these as you want in here, right? So here's my thing, but I'm going to have a small blue right there. But I'm going to take that like, ooh, overpower. And also what you can do here, let me reset it actually, is if you want to have a stronger charge, so let me grids back. What you can do is just kind of stack the charges right on top of each other, right? So, notice the units down there are nanocoulombs. So here's +1. So here's another +1. So that's like a +2, right? And you see it's just generally brighter. And then also, if I put the negative charge over here, you see it's not equal, right? It's definitely more field going on because of this +2 compared to this -1. So it's not equal. You're not going to get the same stuff. However, if I change this to -2, then you can see it looks equal, right? So again, you can kind of mess with this and see how this all works. Now, the lab itself, kind of unfortunately, it's over here. Again, this was made, of course, to be done like in class. So there's a lot of things that ask you to draw what the fields look like. Now you have two options. Your two options for this, neither of them are great. One is to just kind of make a cruddy sort of sketch in like paint. Or honestly, okay, if you want, I'll be nice and you can basically screenshot this. So make the thing in here, screenshot it, and then you can insert the screenshot like into the table. Of course, you have to scale it down or whatever. But that can work in that sense, kind of screenshotting. Or if you just want to recreate it in Paint, that works fine. If you really want to print this out and write it and draw them in yourself, you can do that. But then you have to like kind of scan it back in, which most of you probably don't have a scanner, so that's kind of unfortunate. But again, that's how this can work. So you can see how this, you have, just fields from a +4 charge or a -2 charge. So to unequal, unlike, unlike, that's your design, by the way. So unlike means a positive and a negative, whereas two equal point charges would be like, I don't know, two positives, two negatives. And testing kind of what this looks like. So there's a lot of drawing fields in. So yeah, you can either try to create it on, recreate it with like a kind of cruddy little paint drawing, or if you want to use, just sort of screenshot this, I'll accept that too, because it's, I wouldn't normally, but kind of not the best circumstances. So anyway, there you go. So you kind of mess around with this. You shouldn't have any troubles with this. I don't think so. And again, you can see how this all works. I don't know. I just think it's kind of neat to mess with, and it helps maybe kind of formulate this a little bit better in your head. And it does change, as you move things around, right? So, mess everything up, Anyway, so yeah, I think it's kind of neat. And what you can get is actually, if you can get this perfectly aligned, you could get. Oh, it's annoying they're like in the middle of the grids, but you could get a situation where it's like, okay, so let's see, 1, 2, 3. Oh, wait. I put this right there, and then I put this right here. Oh, because this is here. I need to get rid of these. You go away, and you go away. Yep, you can see that arrow is like almost completely gone. That's showing you that, hey, right there is like a 0 point, right? If I lined them up exactly perfectly, then I would get a 0. So, oh, I need to turn the value. Wait, no, values are on. Oh, there we go. Have to put it in first. 3. Nope. Yeah, whatever. Anyway, you have the idea. Anyway, so mess with this, see what you can fill this out. I do have a wrap-up question for you, also involving this. So the wrap-up question is way down there for some reason. Can this stay up on one page? Nope, it can't. Okay. Explain how you actually can have a total electric field be 0 from 2 charges of opposite sign. Okay, so I said before, I just was talking about how if you have 2 charges of opposite sign, move it here, you can't have a field that's 0 between them. Okay, so, but I'm saying there is actually a way to get the electric field to be 0 involving these 2 charges. Now, the hint is, it's not when you're inside of them. And also, don't just say, well, if you're, like, infinitely far away. Well, then, yeah, okay, fine. But, like, besides that, there is a way to do it. So, think about it for a bit. Again, pause the video and think about that. And maybe mess with this, see what you can come up with, and then come back and write the answer. Okay, so the answer, and I actually mentioned this yesterday, is if you have unlike charges. So let's say this is +2. Again, this is -1. What you can get is you can actually get a region. You'll see here, it's if you get the charges to line up, you can get a region where the field, actually kind of overwhelm this with charge here. Aha, okay, so see here, I'm going to keep going with this actually. Keep going just to really load this up to show my point. Okay, so here they're very unequal, right? But you'll notice, so notice over here the field is pointing to the right, but over here the field is pointing to the left. So there is a 0 point region, like right here-ish. Oh, well, 0.06. Yeah, I was almost at it, basically. So, like, right there, the field's basically 0. And so the field is trying to come in to the negative charge, but because there's so much more positive charge, it's sort of overwhelming. And so you can see how the lines where, like, these lines, they kind of are bending in right here, but these ones just sort of keep going. They bend in, but then they keep going. So there is this 0 point, like, right there. So you can get a 0 point if the charges are one's positive, one's negative, but only if one of them is bigger than the other one, and then your 0 point is always outside of the two. It's not going to be in the middle, right? But it's going to be outside. About there. So outside of the 2 charges, if one of the charges is noticeably bigger than the other one. Well, actually, even if it's just mildly bigger, then you might be able to get a 0 point, but it's just kind of hard to visualize. Here you can see it better through visualization. So there you go. So mess with this lab. Again, I know filling out the lab and submitting it would be kind of annoying. I'll make sure that you have some way of submitting it electronically. Either that will just literally be like an assignment on Classroom to submit it there, or I might have you like email it if that doesn't work for some reason. I'll figure it out. Anyway, this is your thing for that. The only other thing to do is you have so let me actually write the answer here. So if one charge is greater than the other, there will be a 0 point outside of the 2 charges. Okay, so that's your answer with that. Let me clarify this answer, and then... Okay. So yeah, so the only thing after messing with the lab is that there is going to be the Random Science Q&A live stream tomorrow on Friday. So submit any questions into that form that you have. Again, I'll give you a link for that as we approach Friday. It'll probably be early-ish afternoon. I'll give you a bit of more concrete warning. I'll probably say, like, here's where it's going to be. I'll start in an hour, basically, and I'll say when that's going to happen on Friday. So yeah, and again, if you can't make it or you don't want to, it's optional, of course. I'm not going to be like, oh my god, if you're not in the stream, I'm taking off points. Like, no, but just I don't know, to try to have some levity while we're stuck at home and losing our minds. So there you go. Okay, any questions about the lab or trying to get things to work? Please ask because I know this stuff can be a little funky sometimes. But otherwise, yeah, that's it for today. Have fun.